basketball, plumbing, electric cacti, and a random math problem that I thought was cool. What do all these have in common? Mario! But in a sports game, and with random other dudes very loosely connected to Mario. Gosh, does he belong here? Before getting into Mario stuff, welcome to my first Petite Predicament, which, as you can tell, this is truly an original title. This series is just going to be some smaller 4 to 7 minute mini-series if you're just getting into my channel and don't want to dedicate too much time, or if you're a long-time fan and you just want to watch something small. Despite a shorter time span, these videos will still be packed with math. Today's video is a little bit longer than I planned it to be though, so it's more like a Petite Predicament Plus. I'll try to keep them shorter in the future. You know, I had to explain a bunch of stuff and rant about stuff, and that takes time. In this video, we'll be finding my probability of beating an expert computer player in 2v2 basketball in Mario Sports Mix. If you're unfamiliar with Mario Sports Mix, which, honestly, why wouldn't you be? It's a sports game featuring dodgeball, volleyball, hockey, and basketball. It includes some Final Fantasy characters, which, okay. Playing this game first introduced me to characters like Cactar and Ninja, which means I was surprised when I saw Jumbo Cactar on YouTube. I could just see this happening at Nintendo headquarters. Hey, just made a new Cactar. It's really big. I've got it. Jumbo Shrimp. But, Jim, it's a Cactar. Oh, I was talking about lunch. You know what? I'm in a jumbo mood. We'll make it work.
Life tips with Greezy.
Don't name things after your mood. Anyways, we're doing maths today. Going back to 2v2 basketball, I played 21 trial games against expert opponents with a random roster in Mario Stadium because that's the most realistic basketball you can get on this game. Granted, still not that realistic, but close enough. All you need for a really precise measurement is average 2 and 3 point shot attempts and percentages per game for both teams. In these 21 games, I discovered my strategy. Depend on quick steals and to just cast in their eye from anywhere. I shoot an average of 23s per game as opposed to 7 2s per game. This is why I lose with Bowser and Slime. The guy cannot shoot to save his life. A few of the more notable games showed me that it's not just shots and shot percentages that we need to worry about, but also coins. If you score with coins, they are added to your score, and I lost a couple of games just because they cashed in more coins. Let's go over to board for the complete stats. As said before, I shot an average of 7 2s per game at about 44.586% while shooting 23s per game at 42.308%. I had an average of 6 coins per game opposed to the opponent's 7. The computer shot 21 2s per game at a shocking 28.409% and shot 11 3s per game at about 31.25%. From this standpoint, it would appear that I should win every game. I shoot a little less, but at a substantially higher percentage, so I should win every time, right? The only problem is that probability isn't set in stone. For instance, think of March Madness. Before last year, a number 16 seed had never beat a number 1 seed, meaning that Virginia should have had a 100% chance of beating UMBC, but they didn't. The unlikely thing happened, and they lost, so we should account for all possibilities in our problem. This looks like going through all the amount of points either team could get from only 2s or only 3s. For instance, if I shoot 7 2s per game, I could get 0, 2, 4, up until 14 points from just 2s. Let's start out by finding the probability that I make all 7 2s, which is 14 points. Starting at the first shot, we have to make it, and there is a 45% chance of this happening. The second shot is the same thing, since we also have to make it. To make the first shot and the second shot, there is a 0.45 times 0.45 or 0.45 squared chance of this happening. When we add the third, it's 0.45 cubed, and it continues until the 7th shot, and the chance of making all 7 is 0.45 to the 7th, or 0.3505, or 0.3503%. What about if we make 6 shots and miss one? The probability of missing a shot is 1 minus the chance of making a shot, which is about 0.55 here. So all we have to do is multiply 0.45 to the 6th and 0.55 to the 1st, right? Well, it's not that simple. We said that chronologically, the first shot was made, then the second, then the third, and etc. We didn't have to do anything extra because order doesn't matter since made 2s are identical. However, when we add in a miss, the miss could be on the first shot followed by the 6th make. Or the first shot could be a make, the second missed, and the last 5 made. There are 7 spots for the miss to go. Since they all represent 6 made shots and 1 missed shot, we end up with 7 times 0.45 to the 6 times 0.55. Interestingly, 7 is equal to 7 choose 1, or 7 choose 6, meaning that we choose 1 shot of the 7 shots to be a miss. The formula for combinations for n choose r is n factorial over r factorial times n minus r factorial. There's a video on TED-Ed that explains combinations very well. There's a link in the description. This means that for 10 points, we can do 7 choose 5, since we are choosing 5 out of the 7 shots to make, times 0.45, the chance of making a shot, to the 5th, times 0.55, the the chance of missing the shot squared. I suggest storing this as a function of x, since it's a whole lot faster to type in f of 2 than 0.09368. A good formula is f of x equals total shots choose x times the chance of making the shot to the x times the chance of missing a shot to the total shots minus x. You might be wondering, why aren't we using permutations? Don't those solve everything? This is because when order matters you use permutations, but when order doesn't matter, like in this situation, you use combinations. For example, when you're making words, arc is different than car. Having C in the first spot is different than C in the third spot, but if a miss is in the first spot, it's still the same number of misses if that same miss is in the sixth spot. Anyways, we can fill in the rest of the probabilities for 2 and 3 pointers for both teams using our cool formula. Now I will cross out all possibilities whose percentages are below 0.1% because honestly, they don't really matter. Once this is finished, we can multiply all the possibilities for points from 2 pointers by all the probabilities for points from 3 pointers. For instance, if there is a 3% chance of me scoring 12 points off of 2s and a 17.2% chance of me scoring 27 points off of 3s, there's a 0.03 times 0.172 chance of me scoring 12 points off of 2s and 27 points off of 3s, or a 0.516% chance of me scoring 39 points in the game. This takes a while, but eventually we get the probabilities of how many points either team will make in a game. We have to add 1 point to all the expert players' points though, since they score an average of 1 more coin than I do. Sure, coins are variable and weird, but this is a petite predicament. That would take too long, but I might do it later. Now we can use the same strategy to figure out the probabilities for all the possible scores. So whenever we multiply one of my scores by one of their scores, if my score is 2 points or more higher, we can put it in the win category. If it is 1 point higher, we can put it in the tie category since they get an extra coin. And if my score is equal to or less than the opponent's score, it goes in the loss category. After all these calculations, we know that I have a 79.6128% chance of winning, a 2.8314% chance of tying, and a 17.4613% chance of losing. We did take out some probabilities because they were under 0.1%, but even so, the percentages above add up to 99.9%, so each of the answers above can be off by a maximum of 0.1%, leaving them as extremely accurate percentages. Insert ending catchphrase. Hey, thanks for watching. I hope you enjoyed the video. If you like probability, go watch my first Perilous probability video about wordscapes. If you don't like probability, watch some other videos. Make sure to subscribe and tell your friends about my channel if they like math so we can all do math together. We need equal distribution of math, but we're not communist. Subscribe!